All right. Well, hi, everybody. Welcome to the last talk of the workshop. So you've made it. Okay. And for last, but certainly not least, we'll have like Vasilis Syrgkanis from MSR giving talk. So Vasilis, of course, he's an expert in all of the diverse areas of the workshop. So learning in games, machine learning and economics, econometrics, and so on and so forth. And also he's, of course, a lead organizer of the whole semester on learning in games. And today he'll be giving a talk on inference on auctions with weak assumptions on information. Thank you very much, Vasily, and the floor is yours.
Thanks, George, for the introduction. So yeah, I'll be talking about this paper, which is about inference of fundamentals and counterfactuals in auctions. When we don't want to take a strong stance about what information people are receiving before bidding in an auction. One motivating example and the data set that we're actually using in this work is the auctions for oil drilling rights. So there's this open source data set that you can also play with. It's publicly available, where you get data from auctions for drilling rights in Louisiana and Texas. And here we're going to restrict ourselves attention to auctions among only two bidders. So there are 584 auctions among two bidders for drilling rights in Louisiana and Texas. These are oil companies that want to drill for oil, and what we observe for its data point is a bid per acreage. So every oil tract has some area in terms of acres. People submit some cumulative bid, we translate it into bid per acreage. So this is roughly the distribution of bids that you observe in this data set. And the typical approach in these auctions for oil drilling rights is to think of the auction as a common value auction. So there is this unknown common value, which is how much oil is in this tract. And we're each trying to gather information, maybe with different technologies that different companies have before the auction. And then we're going to submit a bid, and the winner wins and drills for oil, and then discovers what was the value for that item that was sold. And what we want to understand from this data set is what is the distribution of this common value in this population of auctions that were run in these two states. So, on average, how is this value of oil tracts distributed? Maybe we can use this information to set appropriate reserve prices, or maybe redesign our auction. So we might want to understand this distribution of the common value, or some summary statistics of that distribution. So how do we go from this distribution of bids to the distribution of common values is the main question. Now, in order to be able to do that, you need to make assumptions that will connect the distribution of values that your bidders know when they submit a bid into the distribution of bids. But this mapping from the distribution of values to distribution of bids is also heavily dependent on the types of signals that each player receives prior to bidding in the auction. So maybe one oil company has different type of drilling inspection technologies than others, or they know something more, and they've inspected and found some more information about the item. And these technologies are typically secretive technologies. We don't know, maybe they're proprietary, so we don't know what they're using. So they receive these signals that we don't observe in our data, neither the auctioneer observes when running the auction. And the mapping from the distribution of values to the distribution of bids is heavily dependent to this signaling structure and this information structure that happens prior to the auction. So if you want to have some more mathematical formalism, we're going to assume that we have an access to data from a common value auction, where the value is drawn from some unknown distribution pi. Pi will denote the density. So with B, we're going to denote the profile of bits that are being submitted. We'll assume that the players have quasi-linear utility. So their utility will be this unknown value minus their bid when they win. It's going to be a first price auction, which is typical in these procurement auctions. And prior to the auction, each player receives some signal Si, which is dependent on the unknown common value. And so it's drawn from some distribution D of V, which depends on the unknown common value V. And then based on that signal, the bidder submits a bid, which depends on that signal. Of course, it doesn't depend on the unknown common value because neither the players know the unknown common value. They only know their signal. And we assume that the data that we observe is an outcome of some Bayes-Nash equilibrium of this incomplete information game, which means that in expectation, if I condition on my signal, my bid is the best response to any other bid that I could have submitted. And throughout the talk, we'll assume that bids and values are discretized. So there's a finite number of bids and a finite number of values that players will have, which will go into the technology that we'll develop. So our goal is to perform robust inference on this distribution of values without assumptions on the signal structure that the players receive prior to the auction, because that's something that we do not know. It's proprietary, and we don't want to make some strong assumptions and then make non-robust, sensitive inference that is only valid under those assumptions. Of course, we're going to be conservative, but we want to be sort of robust to all of those, the things that we do not know and cannot model. So then, if we want to do that, the question is, what are the joint distributions of values and bit profiles that can arise at an equilibrium of the game under some signaling scheme? Okay. If from theory we could, from equilibrium theory, we could pinpoint what is the relation between what is this set of joint distribution. We could pinpoint what is this conditional distribution of values conditional on bids, and let's denote that with some density x. Then we can combine it with the observed bid distribution, let's call it phi, to get what is the value distribution, right? Just simple marginalization. Right? So we're hoping from our auction theory to tell us what is the space of feasible x's that will arise in this game under some signaling scheme. So then, the main question is, what is the space of possible such joint distributions that are consistent with Bayes-Nash equilibrium under some signaling scheme? Okay. And luckily, before our work, there's this beautiful theory by Bergemann and Morris that exactly characterizes what is the space of such joint distributions that are consistent with a Bayes-Nash equilibrium for some signaling scheme. Namely, what they do is they define the notion of a Bayes-Correlated Equilibrium, which is a joint distribution over values at bid profiles, such that if I take an expectation with respect to that joint distribution, and I condition on my bid, I don't want to deviate to any other bid than the one that was designated by this joint distribution, right? So it's a Bayesian version of a correlated equilibrium, a particular one. There are many versions of how you can extend correlated equilibria to games of incomplete information, and this is one definition. But the beauty of this definition is that it coincides exactly with the space of joint distributions that could arise at some Bayes-Nash equilibrium for some signaling scheme of this original incomplete information game.
So is there a prior over V that is incorporated with psi? Does the margin of psi on V equal to that?
Yes,
prior?
exactly, yes.
I see. So for every prior, there is a set of psi's.
Yes. So there's this extra consistency also a requirement. So this is the main, like the main observation that we're gonna also base our inverse sort of like exercise. And the main contribution of this work is to use this beautiful machinery of Bayes-Correlated Equilibria and apply it to the econometric question and develop an informationally robust inference process that boils down to solving a stochastic linear program. So the main observation, the main contribution of this paper is that if you're searching for the space of all possible value distributions that are consistent with the observed distribution of bids, and such that the observed distribution of bids is a Bayes-Nash equilibrium under some signaling scheme, then equivalently, you can ask, what is the space of possible value distributions that are consistent with the observed distribution of bids, and such that the joint distribution is a Bayes-correlated equilibrium? The two questions are basically identical. And so then you're looking for such joint distributions that correspond to a Bayes-correlated equilibrium. So they satisfy all of these best response inequality constraints for every bid of a player and every deviating bid. And then the extra thing that happens is that you want this joint distribution to also be a product of the observed distribution of bids and this marginal distribution, this conditional distribution of values conditional on bids. And so the only unknown over here is this X thing that we do not know. Phi is something that we observe in the data. This is coming from the rules of the auction. And so the X that we were looking for, the space of X's that we were looking for, is exactly the space of X's that satisfy those inequalities for every I, Bi, and Bi prime.
What's the signal scheme and how I guess you're taking it out of the picture here, right?
Yeah, it's because of that the theorem of this theorem that you don't, if you're just looking at how values and bids correlate with each other, and that's the abstraction at which you want to look at correlations. This theorem exactly gives you the space of all possible sort of correlation structures, and you don't need to actually, like for every correlation structure, you can find a signaling scheme that will support it, and vice versa, and that's what this gives you. So you don't really need to argue about the explicit signaling scheme. It's implicit. There is some kind of construction of a signaling scheme that will support the correlation that you sort of impose.
So you can just see how you can go from the correlated equilibrium to.
If you read their paper, yes, I don't remember. Like it's in the proof. Yeah. Like it's something like you receive a signal that's your bid or something like that. It's something, right? So it's like a relation type of principle, right? So you receive a signal that says bid that, and then. All right. So, as I said, this is something that comes from the rules of the auction. Let's call it Q for simplicity. This is something that you observe in the data from the bid distribution, and this is what X needs to satisfy. And then once you satisfy those constraints, you can also back out what is the distribution of values. Right? It's this another linear constraint that will give you the distribution of values part. And so this is sort of like, if you want to take one thing away from this paper, is that you can do econometrics that is robust to inference, so robust to informational assumptions by solving this linear program. Right? So this is a linear program where X, V conditional on V are and pi of V are the variables. So because we assume that values and bits are discrete, there are going to be as many variables as the number of values and the number of bit profiles. And here the number of values, common values. And the space of all possible common value distributions is the space of feasible solutions to this LP. And so the identified set of value distributions is the set of feasible solutions to this LP. So that's the main framework. There are several, given that, like this set of feasible solutions to the value distribution is given by an LP, there are many other nice things that you can do with it. And so, the other contribution of the work is to give you several other things that you can do with this observation. So let me give you some other things that you can do. One is that because your feasible set is just a polytope, you can minimize or maximize any linear objective of that density. Right? And so you can find upper and lower bounds to any moment of that distribution by solving a linear program.
I'll by my previous question and your answer. So is pi known?
Pi is not known. Pi is what you're trying to reverse engineer. In the original, when you're going the forward direction, like what they,
the agents.
the agents are like, the Bergemann and Morris work was more like, I give you some pi, what is the feasible joint distributions I should expect? It's this joint distribution and also the marginal on pi. Here we do the reverse. We marginalize on the phi, on the distribution of bits, and yeah.
The other question I was like, how much is this sensitive to the fact that we don't have perfect knowledge of the distribution pi, but we have approximates? If I jiggle this LP, what is the error in my estimation?
Yeah, so that's the inference part. I'll talk about some results on the inference part. In the end, I'll also mention that I think a big open question is finding better inference procedures for such LPs, and you'll see what we have. There's been some recent progress on that topic that I haven't followed fully, and I recently seen on archive. I believe even on next week's causality estimation reading group that's happening on Thursdays. There's going to be one paper that relates to this that Vera Semenova will be presenting on partial identification. Yeah, so that might be a relevant reading group. So we're still in the population regime where we observe the distribution of bits, right? And all I was saying, you can do these nice other identification exercises. You can find upper and lower bounds on the identified set. You can exactly find the identified set by solving two linear programs. Another nice thing that you can do is you can ask counterfactual questions. You can say, what if I change the mechanism? Or what if I change the rules of the game in general? And I care about some objective like revenue or welfare. Can you give me some upper and lower bound of what that objective would look like in this new game if I assume that the players are going to have some other signaling scheme in that new game and they're going to play some Bayes-Nash equilibrium? So this now boils down to exactly adding an extra set of constraints and coupling with the original set of linear constraints, and it's going to be a bigger LP. But still, you can formulate these upper and lower bounds as another, solving again two linear programs. These linear programs are going to now have Bayes-correlated equilibrium variables for the new game. So psi tilde will be a Bayes-correlated equilibrium of the new game. And what you want is to optimize some objective, not optimize, to characterize what is the value of some objective that depends on values and bits. So it could be revenue, could be welfare. That distribution of joint distribution should be a Bayes-correlated equilibrium. These are these constraints of the new game, which is given by U tilde. And this Bayes-correlated equilibrium should marginalize to the pi of V, which should also satisfy the consistency requirements that you get from your original game, right? And so all of these are now just linear constraints, and you can solve these two LPs and get upper, the identified set of some counterfactual quantity when you change the mechanism. So you can ask questions, I'm running a GSP. What if I was running a first price auction? What is the revenue that I should expect to get, right? Or I'm running a first price auction. What if I was running a second price auction? What revenues do I expect to get, given the data that I have from a first price auction? Or given data from a generalized second price auction, what should I expect my revenue to be in a first price auction, without making assumption of what signals players receive, either in the original game or in the new game. Go ahead.
If I don't change the information structure in my counterfactual.
So yeah, good question. So in these counterfactuals that we had in our work, we were allowing also the signaling scheme to change between the original and the counterfactual. You can think of it as, I'm doing something this year and I'm gonna deploy a new thing next year. My advertisers are gonna get some new signals or whatever, so that changes. But it's also, in many scenarios, might also be interesting to ask, what if I couple the information, the signaling scheme? So I constrain the signaling scheme of the bidders to be the same in the new and the old mechanism. And this was a question addressed by follow-up work following up to our work, Bergemann, Brooks, and Morris addressed exactly that question, and showed also that even that counterfactual, you can write it as a linear set of linear constraints. But basically, what happens here is you need to view the whole thing as a single game, and now you have a Bayes-Correlated Equilibrium which submits jointly a bit in this game and in this other game. It should be a joint Bayes-Correlated Equilibrium. So that's why now you're going to have variables that correspond to join the value and the bid in the new game. And so there's going to be some more intricate coupled constraints, how this variable enters in the new Bayes-Correlated Equilibrium and in the old Bayes-Correlated Equilibrium. But you can still use all of this machinery of LPs to address that question too. Other things you can do is you can add some constraints on shape constraints on your density, as long as they fall into some linear set of constraints. So for instance, you can add Lipschitzness by saying that the density between two values is not going to change by much. This is another set of constraints. You can throw it into the LP and optimize subject to such Lipschitzness constraints. So this is if you want to sort of narrow a bit your identified sets. Another set of things that you can do is assume that your density follows some parametric family. So what if I assume that the distribution of values is some truncated normal or some log normal distribution with some parameter? Then I might want to find what is the set of feasible parameters that are consistent with the observations. Right? So now I'm not looking about a non-parametric density. I'm looking about a single parameter. I'm trying to find what are the parameters that are consistent. And then you just add here the constraints. So for any theta that is a candidate parameter that you want to test whether it is consistent or not, you add the density here for theta and you check whether this linear program is feasible. And so for every candidate theta, you have a checker, which is a solution to a linear program, a feasibility, feasibility of a linear program that checks whether that parameter theta is feasible. So if you have a two-parameter family, you can construct a grid of those parameters and check everything, and you're going to include or not include a parameter based on this linear program. So this is more computationally intensive because you're going to solve a linear program for every grid point, but you can also do that, and we do that also in experiments. Another thing is, you might worry that because you're making no assumption at all about the signals of the players, you might be getting very wide identified sets. And so in practice, you might want to restrict a bit how informative the signals that the players receive are. So you might want to say that I don't know exactly what the signals they receive, but I believe they receive some signal that is quite at least this much informative of the common value. And the more informative it is, the more you're going to be connecting bids to values, and the tighter the identified set is going to be. Of course, there's limits of how you can do that while still maintaining the LP structure. One example that you can do is, first you need to augment the whole framework by adding what is known as these minimal signals. So apart from the signals that we do not know, you can also extend the framework of Bergemann and Morris and add, the notion of a minimal signal where players receive those minimal signals too, and on top of that, they might receive something else. And still, you have the same type of Bayes-Correlated Equilibrium constraints, but now on top of conditioning on the bid BI, you also condition on this minimal signal TI of every player. And again, the signal is also going to be part of the fundamental, so you also need to marginalize the signal. And once you augment the framework with these minimal signals, you can now do things like saying, I believe that the minimal signal is going to be within epsilon of the common value. And then it just changes the support of those linear constraints that the signal that the player receives should be in the support that's consistent with the common value, and you get tighter linear constraints. So that's one way you can do that. Another way you can do it is to say that I believe that I impose that these minimal signals will follow some parametric family. So at least the players receive some normal distribution centered at the common value and with some variance sigma squared, and on top of that, they might receive something else. And then, you again get an extra linear constraint, where here Q is a known coefficient, and pi of V is the thing that you're trying to identify. Okay. So this is a way to incorporate the informativeness constraints. So these are all the population quantities, all of the identification strategies, and then you reasonably you ask. Now I don't have this population limit. I don't have this distribution phi of the bit profiles. I only have access to n samples. In our OCS data, it was 500 roughly samples. So we observe n samples of those bit vectors. And the standard approach is to replace this expected constraint with an empirical analog of those. So, if you view this expected constraint, it's basically an expectation where here I have an indicator of whether this random variable b was equal to the bit profile small b. So my constraints, my population constraints are of this form. I have some expected value of some quantity that involves some randomness omega, should be less than or equal to 0. And what I'll do when I have samples is replace these expectations with empirical averages. So I'll now solve the empirical version of those constraints. But in order to account for the fact that I have error in my empirical objective and in my constraints, I will add some slackness to my constraints to account for that sampling error. So you're not going to check whether they're less than or equal to 0. You're going to check whether they're less than or equal than some threshold sigma n, which is going to decay to 0 as n goes to infinity.
So for bit vectors that are very rare or like don't appear at all, you're going to get nothing from this constraint.
Yeah, but if they're very rare, still you get concentration, right? So it's just going to be you're still going to get concentration. You're not looking at the conditional. You're not looking at. You don't care about like sup norms or consistency of the density, right? So you just care about these averages, which yeah. So
I guess
it's more benign than learning the density. Yeah.
I guess what I mean is like if a bit vector is very rare, so you trust this x bit b. Like
you might not, but then also it's not going to enter in the pi constraint, right? That rare. Right? What you also care is about averaging over the right. So it's not going to affect that much the pi when you marginalize on values.
Yeah, I see that. I guess I would be more comfortable if you told me like with this many bit vectors, I can.
Here's what that you can get. If you want to go the route of concentration inequalities, you can say so. Let's look at the non-parametric inference where you don't make any parameter. You care about some moment of the distribution. So you minimize over x the empirical objective. This is just a pi of v, right? I took the equality constraint and put it in the objective, and this is the empirical objective. What you can show is that as long as sigma n and epsilon n are roughly log the number of bit vectors that you have over delta divided by the number of samples, then the set that corresponds to ln minus epsilon n and un plus epsilon n is going to contain, it's going to be a superset of the population LU with probability 1 minus delta. There are also some constants here are, what is the magnitude of the utilities? There's going to be a constant in front of it that's typical with concentration inequalities, but not many more constants. And here, of course, you're going to get exponential number of bit vectors if you have many bidders, but it's inside the log. So it's still going to be polynomial in the number of bidders. And yeah. So that's one result that you can get.
Sorry, what is this?
The number of bid, the number of bid profiles in the support of the distribution of bids. Right? All possible bid profiles, right? So if you have, let's say, for every bidder you allow 20 discretized bids, and you have 5 bidders, this is going to be 20 to the 5. And similarly, if you want to do like parametric inference, so you're saying I assume some parametric family, and I want to check whether some parameter theta is in the identified set. So I want to give you a set which is a superset of the true identified set. And then you're going to solve exactly the same types of inequality constraints with the slackness. You're going to have this also sort of like equality constraint with the slackness. It's going to correspond to two inequality constraint plus and minus, which boils down to an objective of the like a quantity of this form. You're trying to find all of the parameters theta such that a minimum over x, a max over all possible constraints, all of those constraints, this empirical analog of the constraint is going to be less than or equal to some sigma n. Right? So you're trying to choose sigma n such that when you solve this, you get a set that is a superset of the identified set. Again, you can show that if you choose sigma n to be log the number of parameters. So if you do a grid over the parameters and you check all of those, again, number of bit vector profiles, number of number of common values, if you discretize the common values. If you choose sigma n to be that, then with probability 1 minus delta, what you're going to get is going to be a superset of the population identified set. However, so these are finite sample sort of guarantees with high probability. But what we observed when we try to apply this in the data is that typically these types of sigma n choices, these slackness choices that come out of concentration inequalities, led to very conservative, we're quite large, such that the estimated identified set that you're going to get here is going to be a very large part of the space. So almost all part of the space is going to be your identified set for small samples, right? Because you're very conservative on how these empirical averages deviate from their mean. And so we wanted to also develop subsampling based approaches, which are going to be more less conservative, but will of course only have asymptotic guarantees and not finite sample guarantees. And so here's one thing that we applied in the data and worked quite well in experiments and in the real data, was to develop a subsampling based uncertainty based on some techniques, some generic techniques also in econometrics, where your goal is to find what is the distribution of this worst case moment violation among all the parameters that are in the identified set. So we're here now, we're still in the parametric case. So say we have like a two-dimensional, like a two-parameter family with some parameters, say, being the mean and some other parameter being the variance or whatever. And our goal is to find what is the set of mean and variances that are consistent with the observed data. To do that, you need to say, if you look at the population identified set, what is the typical violation of the inequality that you expect to have in the samples for all points that are in the identified set? In the population limit, all those points should have a violation that's less or equal to 0. But in finite samples, there will be one of those points that will be violated. So, okay, so here this would be the empirical average, not the expectation. So you want to look among all of those points that are in the population identified set. What is the 90th percentile of the violation of these moment inequalities when you go to finite samples, in the worst case over all those parameters in the identified set? So if you could get a handle of the distribution of this random variable, again, I want to be careful. So you replace this with the empirical average. And so this now is a random variable where the samples are the random variables. And you want to get a hold of this distribution of this random variable. if someone gave you the distribution of this random variable, then you could choose the 1 minus delta quantile of that distribution of violations as your slackness parameter, and you'll be getting asymptotically nominal sort of coverage with probability 1 minus delta. Okay. So this is an asymptotic theorem that comes from prior work. And so then one thing that you can do to get a handle of that distribution is subsampling. You can construct an initial estimate of that identified set by, say, solving the min-max problem with no slackness. This is sort of like an optimistic estimate of the identified set is going to be very tight. So you find the sets theta that satisfy these inequalities without any slackness on all of the data. And this is sort of your estimate, your initial estimate of this identified set. Then you start constructing subsamples of your data. And for every subsample, you go over that original identified set and you find the maximum violation, like the violation in the LP. The violation that would make the LP feasible. Right? So for all possible parameters in that set, you solve the LP and you find its solution. You know, like in order to satisfy the LP on that subsample for these parameters, you need like a slackness of epsilon 1, epsilon 2, epsilon 3, epsilon 4. That's what you're gonna get. This tau is gonna be what you're gonna get from every subsample, the worst case violation of those inequalities for those parameters in the original theta hat. And then you can use the 1 minus delta quantile of those quantities over the subsamples. That's gonna be a proxy for the those quantities is going to be the empirical distribution of those quantities over subsamples, assuming the subsample size is little of the original sample size, is going to be a good proxy for how this random variable over here is distributed. And so a 1 minus delta quantile of this empirical distribution is going to be sort of consistent with that quantile that you care about. And then you can, if you want to be more accurate, you can then go back and recompute the identified set with this slackness. This is going to give you a wider set of parameters. And then you can go back and repeat this, but this wider set of parameters until you get some convergence where, by doing that, your identified set is not enlarged more and more. Right? So that is the subsampling based process. And these are the two things that we applied in the data. First, we did some synthetic experiment. Sorry, go ahead.
Vasily, may I ask one question?
Yeah, go ahead. Go ahead,
Sorry, I'm trying a little bit to understand. So I have the maximum loss over some functions. Okay, I am applying minimization. I'm trying to understand if that problem is max min of a convex concave function.
Well, the internal thing, min x over max j, is just an LP, right?
Right, I agree. Because
the above here is a grid, right? So this you go over those points in the grid of theta.
Oh, I see.
Right, it's just a grid. You'll see some grids in the next slide, right? You just
I see,
all those points, right? And you solve an LP for all of those points on every subsample, and you just take a maximum over those, right? So I'm not saying that this whole thing is a. Yeah.
Okay, thank you very, very much.
Great. Yeah, so here's one, like Ruiz. Sorry, yes, sir.
Basically, theta hat depends on your data set here. I'm not sure I have a problem of correlation between the fact that theta hat depends on the data set, but maybe there is like the S is subsampled from the same data set. No?
Yeah. This part is not very rigorous, and most of the theorems are asymptotic. So I don't have something clever to say about that. Okay. Ideally, you would want to sample split, but yeah.
Okay.
Yeah. So I think the one open question is getting more robust and formal guarantees for these types of subsampling procedures. There are, if you go to the literature, there are asymptotic consistency rates, not rates, asymptotic consistency properties, but. Yeah. So first we started with some synthetic experiments to understand how these different uncertainty quantification approaches work. Over here, the first thing we try to do is, okay, how much do you gain or lose in terms of like identification power when you don't assume any parametric distribution? So each one of those pictures is a different parametric distribution. So we generated data where we drew the value from some parametric distribution like a Gaussian or Poisson or binomial. Then we calculated some Bayes-Correlated Equilibrium for the bidders for some signal, which corresponds to some signaling scheme. We then drew bid profiles from that Bayes-Correlated Equilibrium, and we asked, what is the identified set given this bid profile? So here we are in the population limit. So we actually you calculate the Bayes-Correlated Equilibrium in terms of like exact distributions, and that's what you then feed into your inverse LP program. And so these are population quantities. So you see here that the brown is if you also assume that in the inverse problem that your distribution is Gaussian, you'll get an identified set that is this brown thing in terms of like the identified set for the mean and the standard deviation of the distribution of values. If you don't assume and you go after a non-parametric specification, then you're going to get the green thing. So the identified set is going to be quite larger, but not that large. You don't get like everything without making the parametric assumption. And the same thing is what we depict in the other ones. So it can buy you a lot of stuff if you make a parametric assumption and it's correct, as well specified, but of course, you might have misspecification problems. The other thing we wanted to understand is okay, how conservative are the concentration inequality approaches. And so over here, you see that so with brown is the parametric identified set that was also showing in the previous slide. And with green is the non-parametric estimated set when you add the slackness that are coming from concentration inequalities. So if you want the rigorous finite sample guarantee, this is the set that you're going to get, the green one, even when n is equal to 1,000. And you need to go to n equals roughly 1 million samples to get something that's sort of reasonable looking. And then we also wanted to look at how subsampling behaves, which is going to be a bit much less conservative. So it might not include the whole set. That's going to be much tighter. On the left again, you see the same figures as before, but in a different sort of like XY space, but it's the concentration equality type of figures. Over here, you see the subsampling based approach, where with green is the estimated identified set. When we have 100 samples, we use a subsample of size 25, and we draw 50 subsamples in that process that I described. And so we get a much tighter confidence set, which includes the brown thing which we want to include. And similarly for n equals 500, you get even tighter. Over here, you see that sometimes you might be losing the brown thing. You might be losing some of those points. So this is a grid. Over here, we've gridded those parameter points, and so you test every one of those. So you might be missing some of those grid points from the brown. So you're less conservative, but you're much tighter, and with 99 confidence sets, you typically always include the truth. Similarly, if you project on the mean of the distribution, you get that you always include the true mean. Also, then signal constraints can buy you something. This is the population identified set with and without signaling informativeness constraints. So here is the more stringent one where we assume somehow that the bidders receive signals that is within two gridded bid points, points from the true value. So epsilon equals 2 means like they get a very informative signal. Epsilon equals 20, they get a very uninformative signal. And we see that you get a point identification when you assume very informative signals, and you get weaker partial identification if you don't make that assumption. And going back to the OCS data, These are the identified sets that we were recovering. So with brown over here is sort of like the zero tolerance set. So this is sort of like what I was saying is the optimistic theta hat, where if you solve, find the points that satisfy all of the constraints with less than or equal to 0. And with green is what you get after the quantile process, where you can enlarge it by taking subsamples and then resolving the LP, but with a larger slackness. And again, you can get some benefit by adding signaling constraints. This is a much coarser grid due to computational constraints. But you know, if you add some informativeness constraints, you can get tighter identified sets. We have several extensions to private value auctions. We've applied it also to sponsored search data, and you know, the whole framework applies to general games of incomplete information with discretized action and type spaces. So you can apply it to your favorite game of incomplete information. One noteworthy application we did was in sponsored search, where this was a private value exercise, where we looked at trying to recover the mean of the distribution of the private value of every bidder. For instance, we looked at 12 keywords and the top 3 bidders on those keywords, and try to find confidence sets for the mean of their private value. The main reason we did that was to try to understand, do we really get humongous confidence sets, or is this very robust but quite conservative inference strategy giving us something meaningful? And you see that you don't get like sort of null sets that are between 0 and 20. So the numbers here are normalized to lie between 0 and 20, and you get quite informative sets for each of those bidders and keywords. And you can even get somewhat informative sets if you do counterfactual evaluation. So we did one exercise of counterfactual evaluation where we're saying, suppose that you were running among the top two bidders of the auction, now a first price auction with only one slot. What is the revenue in that auction? So that's the counterfactual we did. And you get bounds on the revenue. Some bounds are quite uninformative. Again, this should be ranging between 0 and 20, I believe. So you get here some keywords where the revenue bound that you get is between 0 and 10, which is, you know, too uninformative. But you know, you get conservative information of what your revenue could be under if you switch to a first price auction. And if for some of those keywords you get definitive information that is going to be better than your current revenue under GSP, you're safe to sort of switch to that, assuming that bidders will respond. So that was the work. You know, the main conclusion is that we offer an inference process for fundamental and counterfactual quantities that is robust information assumptions in general games of incomplete information with discretized action and type spaces in a manner that can be phrased as a solution to a stochastic linear program. You can incorporate many constraints and variants, such as shape constraints, parametric distribution, and signal informativeness. We developed a concentration inequality-based approach to finite sample inference and a subsampling-based approach with asymptotic distribution guarantees of coverage. I think one main open question is getting better uncertainty set methods that are as tight as the subsampling approaches in the asymptotic limit, but with better and provable finite sample guarantees. Thank you very much.
Thank you, Vasily. Questions from the audience?
Could you said there are many interesting questions in the front of the inference code.
This is what I meant. Like for example, one question is if you just do bootstrap subsampling, can you prove finite sample rates of the bootstrap distribution and how it converges, or do you need to maybe you could do like some smoothing of the min-max objective that would make bootstrap work, and then appropriately take some limits or whatever, you know, like you maybe want to change a bit your criteria to be not be very unstable like a min-max objective, so that the bootstrap will be consistent, and then while controlling for the bias. So showing that some form of bootstrap works in this setting and giving finite sample weights on how the distribution of the bootstrap converges to the true distribution. This is an interesting open question.
I don't know if I didn't get that. I was just curious. Most of the talk, I think, was about common values. And then in the end, you said it worked for independent private values. And I didn't know where kind of the math changed. Or like, did it go as far back as the Bayes-Correlated Equilibrium? Or
Yes, it changes from the very beginning, but with more notation. Like instead of just having a single value, you have a VI for every bidder. You can also show that you can decompose the LP to be only constraints for the VI of a particular bidder if you have independent private values. So then it becomes a similar LP as the Bayes-Correlated Equilibrium, but you have a VI for every bidder separate and a joint distribution of bids B. And more generally, you can do it for any incomplete information game where you have some minimal signaling structure T, you have some fundamentals, fundamental vector V, which maybe some of them, like some of that vector the players observe, like in a private value, they observe their part of the value vector, or some they don't observe. And so there is like what extra information they observe is part of the signaling scheme that you're robust to. So that's the generality of the framework. Yeah.
Question. So when the number of parameters is too large to afford the grid search, do you have any idea of what you could do? Could you do like, for instance, optimization by doing implicit differentiation from the LP?
I would suspect that then more like quasi Bayesian procedures would be things that would work, where you do some sort of Monte Carlo, where this is your criterion is this min max thing, and you do sampling and like some maybe Langevin or whatever dynamics to sample from that. Some form of like that would give you a rough approximation of the identified set. You try to traverse the space and sample from the space. But of course, now your objective will be an LP, so it might be a bit complicated evaluating your objective. Right, your objective will be this min-max criterion. So the thing that goes into your quasi-Bayesian, like likelihood is a min-max thing. So that but that would be my go-to. Yeah.
So are there any conditions, back to the question I asked at some point during the talk, like, are there any conditions under which, like, if you solve this LP, you have confidence in, from samples, you have confidence in the mapping from bit vectors to the X function, the X
thing, or that
yes.
You have consistency in the X.
Yeah.
I've never explored that. I haven't looked at that at all. Because for the quantities that you care, you don't need consistency.
I understand, but in principle, you might care about that quantity.
Yes.
I don't know.
But that quantity is the X is like super partially identified, right? That whole mapping, right? It's all possible. It's the whole polytope in some sense. It's a very, unless you project it into some dimension, it's a very complicated. So first, partially identified is not a single function, right? So it's a space of all possible sort of functions or whatever, discretized functions. So it's a space of, if you think of for every bid, you have a vector that is the number of values that you have. And so that is the dimension of your polytope, the dimensionality of the space, and you're trying to find a polytope in that dimensional space. I don't know, it's a very high dimensional object, and the beauty is that you don't want to characterize that very high dimensional polytope object. The quantities that you care about are simple projections of it.
Right.
Yeah.
I guess, in the sense of like, imagine I see people bidding and I want to understand what's the probability this oil field has a lot of stuff underneath.
Yeah, but I think for that, this type of exercise won't give you anything because you're not making assumptions about what signals they receive.
Yeah, so I guess that was my question.
Yes, so it's not about sampling. It's more like about even in the population, the assumptions you're making are not strong enough to give you particular information about those types of quantities.
Very nice talk. So in your work, you've also done other papers work about econometrics with learning agents. Is there any way to combine these two frameworks here? And
Yeah, I mean, one interesting topic would be if you go to Bayes-Correlated Equilibrium, they have some connection to no-regret learning in incomplete information games. And so you could potentially try to extend these things to inference under Bayes-Correlated Equilibrium which would correspond to what if my agents play no-regret, like some contextual bounded algorithm, where the context is their signal, and you don't make any assumption about what algorithm, and that would converge to the space of Bayes-Correlated Equilibrium, and then you're doing inference under that.
But is there like a similar characterization theorem for that class?
Yes, I mean, we have a paper with Jason Hartline and Eva Tardos at some NeurIPS 2017 that gives you the notion of Bayes-Correlated Equilibrium that corresponds to those limit distributions, and it would be I can't recall on the top of my head if it has any constraint that won't be a linear program. I believe it won't have. That's something to check.
Okay, that's it. Let's thank Vasily and all of the speakers once again. Thank you, Vasily.